Leaving Radiator Springs in the Dust is an episode of the Degrees of Freedom Project videos on chemical and thermal principles. Definitions and additional details can be found in the webpage link in the description. This video explains recycle and bypass in a discussion of some of the basic techniques for use in process flow diagrams and what implications they have on the equations that you use. Typically used in chemical engineering, recycling and bypass work to control or optimize a process happening in a larger system. In the previous video, we explored recycle and compared a process without recycle to one with it. In this video, we'll discuss bypass and give an example of recycle in a process with two reactions. Bypass is much less common than recycle in process flow diagrams, but it does occur occasionally. The most common example is a fruit juice concentrator. The reason for bypass in a fruit juice concentrator is that the typical means of concentrating fruit juice is by evaporating or boiling off a lot of the water. The heat necessary tends to change the taste of the juice quite a bit and give it a processed flavor. If you bypass the concentrator stage with part of the feed and add a little bit of fresh juice to your product, then you have a bit more of the fresh juice taste with it. Here's the diagram showing a typical bypass stream. We have our feed coming into the divider. The bypass stream goes around the separator and joins back up into the mixer. In between the divider and the mixer, we have the separator, which does whatever it is that it is going to do to the through stream. And finally, out of the mixer, we have the product. The equations for bypass are fairly straightforward, since we've gone through the divider equations, the mixer equations, and the separator equations. You can often simplify process flow diagrams by separating portions of the PFD and looking at the inputs and the outputs. If you draw a bounding box around certain of the elements and only look at the inputs and outputs of those elements, you can combine multiple units to become a single conceptual unit. For example, in a more realistic process for the dehydrogenation of propane to propene, you would find that the methane and hydrogen would be separated out by an absorber, which absorbs the propane in the propene in an oil, but not the methane and hydrogen. The mixture of the oil, propane, and propene is fed into a stripper unit, where the propane and propene are stripped out from the oil, which is then recycled back around to the absorber unit. If you look at the dotted box in the diagram, you have one flow stream entering, stream 3, and two streams exiting, stream 7 and stream 4. The compositions of those two flow streams are different, so the bounded area meets the definition of a separator. Here, we show the process flow diagram where we replace the absorber and stripper with a separator. For an overall balance, you can simplify the process further, as we described earlier, by putting a bounding box around the entire system with one flow stream entering, stream 1, and two streams exiting, stream 7 and 6. At this point, we can no longer refer to it as a reactor or separator, but we can calculate flows and conversions. The resulting block shows we can have propane coming in, methane and hydrogen coming out the top, and propane and propene coming out the other side. This block will be useful for calculating the overall fractional conversion, or the overall extent of reaction. Let's look at the calculations for the slightly more realistic dehydrogenation process. We have the diagram here, with the reaction products in stream 3 entering the separator, that is the absorber and stripper together. The methane and hydrogen exit the separator, and the propane and propene exit the distillation column. We previously had one reaction, now we have two reactions. The desired reaction is propane reacting to propene plus hydrogen. We now have an undesired competing reaction where propane plus the produced hydrogen reacts to produce methane, which we do not want. The fractional conversion of propane in the reactor is 35%, and the selectivity of propene with respect to methane is 2. We again label our variables. We have propane as A, propene as B, methane as C, and hydrogen is now D. We could have switched C and D, but hey, this way it keeps you on your toes. This time, instead of specifying the input flow rate, we're specifying the product flow rate, and stream 6 is 100 moles per second, and stream 6 is now 98% propene, so we have 100 moles per second of 98% propene exiting in stream 6. The recycle stream, stream 5, is 97% propane. We'll skip a couple of detailed steps in the solution. If we use our overall diagram, then we see that the propane and propene coming out is 100 moles per second, and it's 98% propene. So that means we're producing 98 moles per second of propene. Since propane is only produced in reaction 1, that means that the extent of reaction 1 is 98 moles per second. Mole balances of B and C give the B generated the difference between the B entering and exiting. The same for C. Since no B or C is entering the process, and B is only produced in reaction 1, and C in reaction 2, the generation rates are the same as the exiting rates, N.B6 and N.C7 respectively. Since B only participates in reaction 1 and C in reaction 2, we can say that the generation rates are the respective extents of reaction times the respective stoichiometric coefficients. Thus, the selectivity is the ratio of the generation rates, which is the ratio of the exiting rates, which is extent 1 over 3 times extent 2, which is equal to 2. Since we know extent 1 is 98, then extent 2 equals 98/6. Now performing a mole balance on the propane, we get the number of moles of propane exiting is equal to the number of moles of propane entering, plus the stoichiometric coefficient of A in reaction 1 times its extent of reaction, plus the stoichiometric coefficient of A in reaction 2 times its extent of reaction. Since we know all these numbers now, we get that 2 is equal to the flow rate in minus 98 minus 16.3. In other words, the entering flow rate is now 116.3 moles per second, instead of the 100 moles per second that we used in the last video. In that video, we specified the feed rate. In this one, we had to calculate it. Now that we've done our overall balance, which is often the easiest first step, it's time to do the calculations around the reactor. The fractional conversion of A, which was given as 35%, is equal to 1 minus N.A3 over N.A2. So, N.A3 equals N.A2 times 1 minus F. In terms of the extent of reactions for the two reactions, which we know, N.A3 is equal to N.A2 minus extent 1 minus extent 2. Setting N.A3 from the fractional conversion equal to N.A3 from the extents of reaction, we get an equation with only one unknown, N.A2. Solving for N.A2, we find it's 326.7 moles per second. If we do the material balance on A in the mixer, the equation becomes N.A2 equals 116.3 plus N.A5. In the reactor, we can solve for N.A3 from either the extents of reaction or from the fractional conversion. N.A3 equals 0.65 times N.A2. In separator 1, we have N.A4 equals N.A3 minus N.A7, which reduces to N.A4 equals N.A3. And finally, the flow rate of A in stream 5 is the flow rate in stream 4 minus that in stream 6, which we earlier calculated to be 2 moles per second. The solution of the set of equations around the loop gives us the following values. N.A2 is 326.6, N.A3 is 212.3, N.A4 is 212.3, and N.A5 is 210.3. Given that the recycle is 97% A, we can calculate the total flow rate in stream 5 as the flow rate of A in stream 5 divided by 0.97, or 216.8 moles per second. Here's the diagram again, with a spreadsheet showing all the flows in the various streams, so you can look at them and see what has gone on there. In the columns are the molar flow rates of each species, the total molar flow rate, and the mole fractions of each species. Problem specifications are in green. For the reactor, we have the fractional conversion, the stoichiometric coefficients, and the extents of reaction. Reference values are in blue. We haven't explicitly included the split fractions in the spreadsheet because they are either 0 or 1. The actual spreadsheet is linked on the video reference page, and that link is in the video description below. The takeaways from this video are 1. Bypass is less common than recycle, but can be analyzed the same way. 2. Often the quickest way to analyze a PFD is to do overall balances and partial balances first. 3. If there is only one reactor with possibly multiple reactions in a process, the extents of reaction are the same for the overall process and for the reactor. 4. If there is only one reactor with possibly multiple reactions in a process with recycle, the overall fractional conversion is almost certainly much higher than the fractional conversion in the reactor. Thanks for watching! This video is brought to you by the DOFPro team.